Thank you very much.
Thank you. Okay, so at the first stage, as I said, in my line of work, we'll only go through two stages, the first and the second. We will remove the scale of the compact object, and then we'll remove the orbital separation scale. At the first stage, we will use the bottom-up approach. What the bottom approach is about thinking about raising the energy cutoff of the theory from something to whatever we want to raise. The way to think about bottom-up is to think about bottom-upping the cutoff energy of the theory. And as we are raising the cutoff energy of the theory, that means that we have to have the theory more and more precise. We have to make the theory more and more complete. So that's the way to get in your head the idea of the bottom-up approach. We start by having the full theory. The full theory is just the pure gravitational Einstein-Hilbert action, or whatever modified gravity action you would choose to start with. And then we think about some abstract decomposition of the field. We think about decomposing the field into the Fourier modes, which are the high energy Fourier modes, or the high momentum Fourier modes, and the low Fourier modes. And then the way that we construct the action in the bottom-up approach is that we just augment the original action with infinite operators that basically we just build an action from scratch without knowing anything. We just look at the problem, we decide what are the degrees of freedom in this scale that we are considering now, with the new scale that we are considering now, the one which is much above the scale that we want to integrate. And what are the symmetries that survive in these scales? And once we identify both of these, and this is actually the hardest task when we do this approach. The hardest task is to identify correctly what are the degrees of freedom and the symmetries. This is where you break your head. Afterwards, it's just technical. And then once you decide what are the correct symmetries and what are the correct degrees of freedom, you just couple it in every possible way, and every way which is allowed by the symmetries would appear here in the infinite set of operators that would supplement the action. Okay, in this case, we would supplement the action by worldline operators, namely those which are located on the worldline, because what we would identify is that from the field that had all the Fourier modes, we now want to have the field that includes only the low energy Fourier modes. So now we'll have some partial field that includes only some of the modes, but in addition we will add degrees of freedom that now describe the worldline of the single object. So if we just consider mass, we will add just the location of the worldline of the object. Once we want to consider higher multiples of the object, like spin for example, we would also have to include worldline tetrads. So this is the EUA. So we add worldline degrees of freedom, and therefore we would add to the action a point particle part, the point particle action, which would be located on the worldline. And all that it should satisfy is that these operators are the ones that should obey the symmetries that we identified, and all the scale dependence that they will contain will be the scale dependence that is now includes only the scales which are above Rs. So no Rs is to appear in these operators, okay? All the dependence in the scale that has been integrated out would appear in what we call the Wilson coefficients. These coefficients that precede the operators that we construct, encapsulating them all the UV physics that we want to suppress. And the fact that this kind of writing the action in this way accounts for the physics correctly just is a very classical canonical result that is usually referred to by the decoupling theorem from Appelquist and Gravitona from the 70s that guarantees us that indeed we can describe correctly the physics at the larger scale by writing operators that include the larger scale and just preceding them with coefficients that encode the UV physics that has been suppressed. At next stage, at the second stage, where we move the orbital scale R of the binary, we will use what is usually referred to as Wilson's approach. Wilson's approach is the direct, explicit way to integrate out field modes from the theory. That is the top-down approach. In this approach, we just start from the known high-energy theory, and we explicitly integrate over field modes that we want out of the theory by the usual perturbative methods that we know usually from QFT. So what we have is as follows. We write the field, we rewrite now the field as an expansion around flat space-time, and we identify it, we decompose it again abstractly to two components. One represents the orbital modes and the other one represents the radiation modes. And we identify the relevant characteristic time scales and momentum scales. The time derivative of the orbital modes goes like the frequency of rotation, whereas the momentum, the separation scale is given by R. So we have here something which is different, because when we consider the radiation modes, these are the modes that represent the actual gravitons that propagate to infinity. The on-shell gravitons that the asymptotic observer measures, okay, these are on-shell, and therefore their frequency and momentum are the same. They go like V over R. They are fixed by the typical rotational velocity of the binary. So they go like V over R. So we recognize clearly that we have here hard modes and soft modes. We have hard momentum and softer momentum. And therefore, what we do now is we start from the high energy theory, but the high energy theory at this stage is the theory that we constructed in the previous stage. Is it clear? Yes, it's clear. Okay. So at the previous stage, we constructed this additional point particle action, and since we now want to consider the system of two particles, we just add a copy of the point particle action for each of the objects. So that's the high energy theory that we begin from. We begin to construct from the second DFT, and on this high energy theory, which appears here, we do the integrating out of the orbital field modes. Okay, we integrate out the orbital field modes by definition, it's defined by the functional path integral, and as we just usually compute functional path integrals, it means just evaluating the Feynman, the diagrammatic expansion by the usual perturbative methods. The only thing that should be mentioned here is that we are handling classical physics, which means that from this path integral, we would only consider the three-level diagrams, namely saddle point approximation, or whatever you want to call it. We will only be interested in extracting the part which corresponds to the classical physics. In order to get the effective action in the conservative sector, there is no need to continue, we can stop here. But we just want to stress that indeed we have to verify that at this stage we are left without any remaining orbital scales to the degree of freedom. And this was something that was not achieved in previous work, for example. Some of you know, for example, Porto's work. That was one of the disadvantages or the shortcomings of his work, that he was not able to split the particle and field degrees of freedom, and therefore the action that he obtained still had orbital scale field degrees of freedom in it.
Sorry, is the final action, does it still have any Bayesian variance in it?
Does it still have?
Any Bayesian variance in it?
It shouldn't have.
Because that breaks.
And because when you compute, you should do some gauge fixing along the way, and then okay. So
Sorry, just a practical purpose. How many fields do you need to compute for effective action? To which order of fields? Because you're doing a flattening expansion, and there are more and more external lines.
yeah.
So usually, how many?
You mean like what level of loops? Like what
No,
level
you're
of
just computing a tree, right? I mean, it's just a tree level.
yeah,
So
but that's
how many number of external fields do you
you mean like in terms of you think in terms of endpoint function?
Yes.
Like what is yeah, but it's not this, yeah, you're thinking like QFT and that's not QFT. So but we will have loop intervals, so that's the point I was trying to make. We don't have loops in gravitons, but we are doing nonlinear theory, so everything is analog. We have loops, but they're just nonlinear H bar. The loops are in G of the square root of G of Newton. So, like I would say, that to answer your question, at the moment they are at the most advanced thing is the for loop, and even there, like not everything is complete.
I'm not talking about loops, I'm talking about the number of
About the legs,
Yeah.
you're thinking, but there are no legs in our case because we have classical sources and the boundary usually.
Oh, I see, it's like boundary with
Yeah, usually you have boundary conditions on momentum. In our case, it's not like that. We have classical sources, and boundary conditions are on the position. They are like you think about the world lines as givens. The positions are given, and so we don't have legs. So we don't think of it like that. So the thing you should think about is what is the highest self-interaction vertex that I have inside the interaction. So the answer is 4. You would see. Okay. So we have to.
Sorry, in the previous constraint, you also including the particle action.
Sorry?
You also including the particle action in the ice level, right?
Yeah.
Then later, unknown Wilson coefficient. Okay. How do we determine unknown Wilson coefficient?
How do we determine the Wilson coefficient? That's a very good question, which luckily we kind of could avoid so far. Because if you just consider mass, the first Wilson coefficient enters at 5 p.m. and we're not there at the moment. I mean, even 4 p.m. I'm not sure if it's at the moment. And with spin, there are Wilson coefficients that come. Okay, so it's divided to 2. When you have black holes, you basically the Wilson coefficients are trivial because you have no Newton physics. So basically, we will frame everything in terms of Wilson coefficients. You will see them in the expressions later, but they are just equal to 1 when you are talking about black holes. And in all the detections that were and are expected in the near future and in the less near future, it will all be black holes. So, like generally, you shouldn't worry about it too much now.
But the event black hole is not one object, so you should have high order to take care of the size. You should have high order Wilson coefficient to take care of the size of the black hole.
You should have.
Because this is the particle action. This is approximation to black hole as a particle.
Yeah.
So the leading is more than the mass of the black hole. But the size will be coming to the high order of Wilson coefficient.
The finite size effects?
Yeah.
Yes.
Then how do I determine this come as a boundary condition or is it unknown coefficient?
Okay, and we're mixing two things. One thing is that if it's a black hole, usually the coefficients are trivial. But as I said, if you just consider mass, it's anyway it enters at 5 p.m. So people don't worry about it because it's anyway they are not at this level of precision of computing. Well, like they hardly got 4 p.m. recently. And when we have spin, actually spin gets in Wilson coefficients at an earlier, at a lower precision. So the first Wilson coefficient actually enters at 2 p.m. from spin effects. And at the moment, I mean, there has been numerical studies that computed this. I mean, they didn't call it Wilson coefficient because it was in the old traditional context that it was done. So there are some estimates to it. But anyway, as I was trying to stress, and I will show again, when you're talking about a black hole, this is just one. There is no Wilson coefficient to compute. It's only relevant when you consider an actual, like a neutron star, for example. So, and we are not there. It will take some time until they will detect neutron star. So that's kind of less urgent to think about it. It's important to think about it, and it's definitely the most challenging part when somebody does EFT, usually in particle physics. Computing the Wilson coefficients is the most challenging part of the work. But luckily, we can kind of avoid this challenge for the moment. So it's like not, at the moment it's kind of an academic question. Like if I say that I'm interested in, because I actually say that I'm interested to compute the Wilson coefficients of spin, that's like, whoa, that's like very academic and very far away, not very urgent. People in LIGO won't care about this much. Okay.